Let's step through implementing the entire linked list. So remember, our linked list has a doubly linked node. Linked nodes have pointer next and pointer previous. The linked list has a pointer first and pointer last, and an item count. So that's a lot of what we'll be working with here. So first off, our constructor sets these to null pointer. Over here, these constructors, for the doubly linked list node, needs to set it to null pointer as well. Set your pointers to null pointer when you're not using them, and item count to 0. Now let's just implement clear right off the bat, because we're going to need this. So don't forget to uncomment out the clear, otherwise it's when the linked list is destroyed, the memory won't be freed. So if you don't have clear commented out, while you're running the unit tests, it's just going to allocate a bunch of memory that should be cleaned. Now, clear requires basically just popping everything off of the list. So, for instance, we can have any kind of list to say we'll have a linked list, and we might have a few nodes. And then these nodes, they all have their pointer nexts and their pointer previouses. And then linked list points to the first and the last item. So I'll just keep reusing this for all of our little things. So this is next, this is previous. So when we are clearing the list, the easiest way to just clean everything out is to iterate through everything and just destroy it. We're going to implement a pop front and a pop back and a pop at. So we could just say keep calling pop front until the list is empty. So that's all we really need to do in this case. While we have is empty, while not is empty, we're gonna just call pop front. So now that means I need to also implement is empty and pop front before my unit tests will actually work, because if these don't work, when you run the unit tests, it'll trigger a not implemented exception. So down here, that's already done. So let's go back up here. To pop, did I say pop back or pop front? Pop front. It doesn't matter which one you do. So let's just think about pop front at first. And normally I might go over like push and pop and then get in that order, but since we have to implement one of the pops in order to actually clean up the list, let's go ahead and do that. So with pop front, we're going to have several different scenarios. We're going to have two scenarios that we need to look out for. So let me just copy this linked list, and we have the option where we are removing the very last item. So if we are removing the very last item, we need to clean up the linked list, update these first and last pointers. So this is going to be our pop to front for now. And I'll just copy these guys for our different examples as well. So with pop front, first, if the linked list is just completely empty, and we know that if first and last are pointing to null pointer, or if our is empty function is set to empty, in this case, we can't do any pop. So we'll just need to decide, do we want to ignore that basically error state, or do we want to throw an exception? So usually most things will kind of just ignore if you're trying to pop from an empty list. You could make it where it throws an exception, but I think with the list object in C++ in the standard library, I think it just kind of ignores it. I could double check that. We could double check that. So if we did like a pop back, the function never throws exceptions. If the container, well, is not empty, it doesn't throw exceptions. Okay, maybe it does throw exceptions if it's empty. Well, either way, I feel like the kind of default behavior would be to just kind of ignore it. So what we're gonna do is, let's say if is empty, well, then we'll ignore. Otherwise, so we have 3 different cases. If it's empty, we're just gonna ignore it. Don't even do anything. If we have our very last item in the list, so this guy is our last item and we're removing it, we're just going to delete this, which we can access through either the first or the last pointer. So we're going to delete him and then point these two to null pointer. So over here, we're going to say if size is 1, or we could do if m item count. Let's go ahead and just double check on size. This isn't implemented, so we return m item count. And we'll get back to the up front. So if size is 1, we're removing the last item. So again, via pointer first or pointer last, we can access that last item. So we delete m pointer first. And we need to update these pointers because currently, even if we delete this one, they're still pointing to that memory address wherever it was at. We've just freed the memory there. So they're still pointing to that memory address, and that's going to cause a problem if we see that and it's not an old pointer and we think that that's a valid address, but it's not a valid address. So that causes a whole problem. So we need to update the pointers. M pointer first should be null pointer. M pointer last should be null pointer. And we need to decrement the item count. And I'll just do this here right next to this scenario instead of out here because I want to make sure that I don't accidentally call m item count minus minus from when it's empty. There are different ways you could do this. If you just returned here, you could put item count down here, but I think that makes it harder to follow the program flow, so I like to keep these like things together. And then the else case is basically you don't have one item left. So it's not empty. It's not the last item. We have at least 2 items in our list. So with pop front, what we want to do is we're going to get rid of this guy, but we also need to point first over here, and we need to make sure this guy's pointer previous is now null pointer. So over here, oops. So we don't want to delete the pointer first right away. We will eventually do that. But if we do that, we'll lose access to this guy. So first, we need to keep track of who that second pointer is. We can either work with m pointer first, m pointer next. We can just use this. Or if we want to make things a little bit clearer, maybe it's easier to follow, we can say doubly linked list node t pointer new first is equal to this. So that doesn't allocate memory or anything. That just gives us a pointer that we can have a nicer name for the new first. So we have new first. We could delete first, then here, m pointer first will now point to pointer new first. And we need to make sure that this guy's pointer previous points to null pointer. So what we've done is we created a little pointer just to point to this as the new first. We can then delete this one, and then we set this one as the new first, which ends up pointing it in both of those places. I mean, pointers, when you assign a pointer here, it'll just take the address that it's storing and it'll point there. And then we set its previous to null pointer. So that's what we do for our pop front. Let's go ahead and build it and make sure things are running. and check those tests. So run to list. Okay, so I have a seg fault in test size, which I could look up. So we have size, list of items, 3 should be 3. If I go into my tests, I can kind of look up the same test here. If we set the item count, and then the size is, well, it's probably after the test itself because the test was printed properly. So it must be the next set of tests that are crashing. Let's go ahead and open the linked list tester just to see what we have. So it crashed at some point, so this is not a complete list. But we have is empty and size pass. The summary, for some reason, is not getting output. You know, I don't know if you want to step through this with me, but we can kind of pause this here, and it did not like, that was pointing to null pointer for some reason. Did I set it to the next item? I did. So we can say new pointer first, m pointer first, and m pointer last. So we don't really need that, but we can look at these. So I think this is crashing when we run the destructor. So basically, it doesn't really matter about the test. We are just leaving the linked list scope, so we end up calling clear, because it's the destructor, that calls pop front, and the first time we're popping front, it's causing a problem. So we can at least kind of double check this stuff. So I'll go ahead and set a breakpoint there, and we'll do this, and we'll check this out. So we have our pointer new first. This is, okay. There's the address of, is this pointer first? Yeah. There's the address of pointer first. We could also look at m pointer first, m pointer next. So this one, I open up that little thing. Okay. So this is the next guy. This is the address. And this will look a little bit nicer in Visual Studio, but that's fine. So first and next. So pointer first should keep pointing there. Pointer, I'm sorry, pointer new first should keep pointing here. Pointer first itself should then be destroyed, which isn't going to update the address. It's just going to delete that memory. Now we're updating pointer first to point to this address instead. So then, let me see, pointer first, pointer next. Wait, something weird is happening, possibly? I wish it wasn't showing all of this data. It's down here. So 30, 70. Why is it pointing to the last guy now? And then we have new first. Okay, wait, yeah. So we updated pointer new first. Let me just rerun this and I will label it as we're going through this. So let's open, what's that? We'll open up the blah, 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 the graphic, the thing I'm drawing in. Okay, so in this test, I believe I have 3 items anyway, so let's just look at these. And the memory addresses change every time, so we'll rerun this from the start. We have pointer first is D0, pointer last is 70, pointer first, pointer next is 30. Okay, and we have new pointer first. We're about to change its value with this line. So we're gonna step over, and I accidentally mounted that. Okay, there we go. Don't do that. Okay. So now new pointer, new first is pointing here. And we're gonna keep going. We've deleted pointer first, so this address is still D0, but we've deleted this. Pointer first should now be the new pointer first. So where is it? New pointer first and pointer first. Okay, new first is now this. Pointer first, pointer previous. So pointer new first and pointer previous is still pointing to this address. So this is our new first at this point. So we have this pointing this way. This is still pointing to this memory address, which we don't want. So then we are going to delete that. Okay, so the first item being removed was successful for the pop front. So let's see what happens with the next one. Yes, this is how you debug. It just takes a bit. So go back up there. The list isn't empty. We're going to pop again. So we have size, and now we have state where this one doesn't exist anymore. And at the moment, pointer first is pointing to 30. I guess I could have left those labels. Pointer last is pointing to 70 or 70. And we're going to set new pointer first to the next item. So technically our new first is pointing here. So we're going to delete. Happen. Oh, we get out of the node. We don't need the node. We're going to delete the current pointer first. And we're going to set the lists first to this one now. So lists first is now 70. That'll go over here. And then we're going to set the new first's previous pointer to not point at 30, but to point to null pointer. So our current first is 70. Pointer first, let's just say this one. All right. M pointer first, M pointer previous. It's still pointing to this, which we've freed. So we're going to point it to null pointer. So that seems to work okay. And we'll go into pop again. So this is the very last item. So actually it's crashing, I think, later on. So this one doesn't exist anymore. Now our first and last are pointing to 70. Not empty. Okay. Size did not... you know what? I see the error now. So even though this is our last item, size didn't trigger for size 1 because I forgot to decrement the item count. And that's what our tests are for, debugging. So now we'll run the tests again. Okay, now it doesn't crash and we get all of the tests running, but they don't all pass. So we have size is working proper now. Get front, get back, blah, blah, blah. Pop front. These tests all pass now that I have the item count decrementing correctly. And we'll try not to make that same mistake for pop back. Okay. So I'm going to copy pop front because it's going to be similar for pop back. Just get rid of this part. And for pop back, we're going to have a similar situation. So If it's the last pointer, we're just going to do the same thing. We can keep is empty, is size 1, that's fine. The pop back here, if we aren't removing the last item, we're going to remove this one, which means we need to update the last pointer, and we need to update this to null pointer. So remember with the pop front, we did kind of the opposite. We updated this and updated this to null pointer. Okay, so see opposite sides, and we're working with a next pointer instead of a previous pointer, and we're working with last instead of first. So they're kind of like inverses of each other. So let's say pointer new last is going to be m pointer lasts, m pointer previous. So just for reference, I'm going to comment out the old version. This is pointer new first. Pointer new last is our current last's previous item. So now we have new last is pointing here to the second to last item. We're going to delete the last. So we'll just delete this one. We're going to update who the new last is. So we're going to point the list's last item to our new last. We're going to set its next pointer to null pointer, and then we decrement the item count. So now if we look at pop back, these tests all pass. Okay. Let's work with the other fronts and backs before we get into the ats, and we'll kind of do all of those at the same time. So next, let's look at push front. So with push front, I'm gonna change this around. Oop. Just erase stuff. So this is gonna be front, back, and at, which we'll do later. So for push front, we either have an empty list that we're starting with, so these would be pointing to null pointer, or we have a list that already has stuff in it, whether it's one item or multiple items. So we're going to need to account for these scenarios as well. Okay. Over here, we'll need to say if is empty, otherwise, and I don't think there's any error checks we need to be doing because we're just adding stuff, we're not removing anything. So if the list is currently empty, well, either way, we're going to have to create a new node. Let's just call this new node. And we'll set its data, and we have a pointer previous and next. So this needs to go into the list. If it's the very first item of the list, we just point this here and point this here, and then we're pretty much done. So we can actually create this outside of our if statements because we're going to add a new node either way. So we'll do doubly linked list node. New node is equal to a new doubly linked list node. So we're actually allocating memory here, which is why having the pop functions is important, so we can deallocate that memory. We also need to set its data. New nodes m data is equal to new data. And then if it's empty, we'll just say m pointer first is pointing to new node. M pointer last is pointing to new node. And we need to increment the item count. So we could go ahead and do that down here. our node count and item count. We don't want to do this ahead of time because that's going to mess up the is empty check. So we do this afterwards, or we could do it inside here if we wanted to. But that is going to be our push front for an empty list. If we are pushing into a list that is not empty, we're going to add it to the front. So this will be our new front. And so what we'll need to do, this will need to point here. This guy's not the front anymore, so it's going to point here as its previous. And this one's next is going to point there. So we'll end up with this in the lists' sequence like that. So our new node is the new first, but before we set that, if we just update this pointer here, before we have this relationship established, we're just going to lose track of this guy. So we need to make sure to not lose track of that guy first. Currently, this is pointing here. We can say pointer firsts, pointer previous, points to the new node. Okay, so we have that. We can say new node's pointer next points to the current first node. And now that that is established, we can set this to point here. So we update the m pointer first is equal to new node. So again, run the unit tests. I guess technically, maybe they're not quite unit tests because the functions rely on each other somewhat, like with a destructor, but better than nothing. Push front. Now those pass. And we'll do the same thing with push back. Copy this. Okay, this can stay the same. This can stay the same. We're just going to do something else here. So instead of pushing to the front, we're pushing our new node to the back. Last items next needs to go there. New nodes previous needs to go there. And we update the last pointer to go there. So here we had pointer firsts. New previous is the new node. In this case, we're working with last. Pointer lasts. New next is that one. So pointer last, pointer next is new node. New node's pointer previous is the current last, and then we update the last to point to new node. Okay, so good. Something didn't go right and it crashed here, but our pushback passed. Well, it threw the not implemented exception, but maybe it wasn't expecting it in the test wherever it happened. That's weird. So we don't need that breakpoint, but in this case it crashed in the push at function. It checked if it existed, and then I don't know if it went into the next one. We'll just do a check real quick because I want to make sure it's not going to affect anything. No, don't go into the string. Okay, for some reason, aha, I have an error in my test here. So technically this should be push at, and now I have another thing to put in my notes to fix. Okay, so that should take care of that. We run this, we got pushback is implemented. Now let's do the get before we start on the ats. So coming up here, get front. When we have just some basic lists, we'll need to check if it's empty first because we can't return data, this whatever data type that is, we can't return anything if the list is empty. So we need to throw an exception in this case. So if is empty, we'll say throw, and then which exceptions do we have? I think I have structure empty. Yeah. Structure empty exception. Let's just say this is the get front. Cannot get from empty list. Okay. Have our else case. If it's not empty, then we can gladly just return the first item. So in this case, we just say return m pointer firsts data. Because the user or the other programmer who's using our linked list does not care about the node, they just care about the data it is storing. So we return that data. Let's go ahead and implement get back. In this case, it'll be just m pointer last. Go ahead and run. Okay, so where are they? Get back and get front now pass. Just have this. This is technically get out. I don't know. That's weird. Another thing to fix. These are technically supposed to be like the same thing because I did not implement subscript operator, but I think this is all we have now is the ats. Yeah. Okay. So with the video we originally posted, we did get at first because it's kind of the easiest and we can build everything else off of this. So with get at, and that takes some index. So even though these aren't in an array, we can think of these as 0, 1, and 2. We get some number. So if we end up asking for position 0, we can just tell them to go to get front instead. If they are asking for the last item, which is the item count -1, we can tell them to go to get back instead. That way we don't have to re-implement the same information. I know it's like one extra function call, but we might as well just tell them, hey, you're just asking for the get front or get back. Let's not do that. Let's just give them the function itself. So if index is 0, then we're going to say push, return, not push, get front. Else if index is equal to m item count -1, we're going to say return get back. It's not going to be item count because here we have 3 as the item count, but 2 is the last index. Otherwise, we also need to make sure that the index is valid. So if it was like 5 or -1, neither of those are valid. So if, else if is invalid index, we'll throw an exception, invalid index exception. And we will want to make sure this is implemented correctly. So currently it's not. What is an invalid index? Well, if it's less than 0, so 0 is always a valid index. If it's less than 0, or if it's greater than or equal to technically the item count, because we got 3. If it's 3 or greater, that's invalid. Now, you could do this. Return true, that's invalid. Return false. But you can also make this shorter. You can say return that and get rid of this stuff, and that will return true or false. Okay, so we got that. And let's go to this again. So if it's invalid index, we just do that. We can put an else case here. This will be get item with index at middle-ish position. So, you know, we could have more nodes than this. It just means it'll be one of the middle nodes. So in this case, we need to get to the node they want, which means we need to walk there. We need to create a little pointer current or a pointer walker to start at pointer first, and then keep moving forward until we get to the correct index. So we're going to create a doubly linked list node, pointer current, and we're going to initialize it to pointer first. And we can either use a while loop or for loop, but basically, if they want, let me do another graphic. Let's say we have multiple items. So there's 0, 1, 2, 3. Let's say they want to get 2. So get at 2. We need to start here, and we're going to start there, going to iterate. So are we at 2 yet? No. Are we at 2 yet? No. Are we at 2 yet? Yes. And then we work with this guy. So for int I is 0, I is less than index I plus plus. That should iterate us. I is 0. Nope. Okay. Is I less than 2? Yes, we're going to keep going. So I is 1. I less than 2. Keep going. I equals 2. I less than 2. No. Then the loop ends, and we'll have our pointer current pointing to this middle node somewhere. So in order to actually do this walking, what we have is, pointer current starts at pointer first. So in our list, this is the first guy and this is the last guy. And each of these have their pointer for previous and pointer next. So if we want to go from 0 to 1, we need to go to its next item. So we can say pointer current is equal to wherever it's currently at, but the next thing. So then that will update the pointer from here to here, and then this will be pointing here. And when we move forward again, we can say pointer currents, pointer next, and that will take us to the next item. So pointer current is equal to pointer current, pointer next. Over down here, at this point, we are at the correct index. You can say pointer current is at the index. In this case, it's pointing to a node and we want its data. So we just return the data. Return pointer current m data. Okay, so let's go ahead and test. So get at, that's all passing now. Okay, so with push at and pop at, we're going to need this same code. So let's copy all this. Actually, let's copy all of this for now, but we'll modify it, but we still need these checks. So let's look at push at. Right here. Okay, we're not going to need this part, but we're going to work with the rest of this. Okay. So with push at, we're also going to need to create a node and set its data. We're going to steal this part here, and I'm going to put it inside of the else case. So what we're going to do is we have just some new node. So this is new, has a previous and a next. We've just kind of created it out there. It's not associated with anything yet. And we're doing push at. And we have a number. So again, this is going to be 0, 1, 2, 3. Let's say we want to push at this position. So it's going to have some value and 2. So up here we have the value that it's going to store, and then the number, the index. It can be 1, 2, whatever. So this is the state of the list currently, and we've walked to index 2. So we also have our little walker node. Let's call this current. and it's pointing there currently. So what are we going to do? When we're pushing at position 2, we want to add this guy in here, and then we still have the item 2, we still have item 1, we just want these to kind of update so that it's in the middle. So current is our basically after, and current's previous is before. So let's go ahead and make a little alias for it just because it'll make it easier. I'm going to go ahead and create a doubly linked list mode pointer. Pointer before is equal to pointer currents m pointer previous. So we have basically the before, and this one is the after. Pointer current is going to be after. So if I split this up a little bit more, see if I can move these a little bit. Okay, just a second. What we're going to end up doing is we want to take our new node, and it's going to go right in here, and then we're going to update the pointers accordingly. So we have our before, we have current, which is after. What do we need to do? Well, we're going to change up these pointers. Let's see which layer I'm on. There we go. We're going to change this guy's next. It's not going to point to the after guy at the moment. We're going to change its next to the new node. The current guy, we're going to change its previous. We're going to change its previous to the new node. And then with the new node, we need to change its previous to before and its next to after. So then what that gives us is a new linked list. This will be at position quote unquote 2. This will be 3. This will be 4. And there's not a formal number system for these. You know, remember that there's no numbers we're setting as indexes. We've just iterated twice to get to index 2. So over, make it small, throw it over here. We have pointer before, we have pointer current is the after, and we have our new node. So we're gonna update neighbor pointers. Say pointer before, its new next is the new node. Pointer current, the after item, its pointer previous is the new node. New nodes, pointer previous is the before, and new nodes pointer next is the pointer current. And we need to not forget to increment item count. So let's go ahead and make sure that works. I put new data, but for some reason I named it new item right here. We'll just change that to new data. And it says return these right here. So I need to update these. I forgot to. If they're going to try to push at index 0, that means they're just doing a push front anyway. So we'll say push front with the new data. Now, item count -1, that's not what we need for the push, because if we're inserting a new item, here we have 1, 2, 3, 4, 5 items, and if they want to insert at position 5, they're inserting to the back. So if index is item count, we say push back with the new data, and otherwise we throw an exception. Okay, and over here, let's see, push at, these are passing now, and now we just need pop at. So again, I am going to go to my get at and copy that, because we still need this whole walking deal. And then we're going to go to pop at and work with this. So in this case, if we have pop at some index, we're going to do the whole walking thing. If they said pop at 0, we're just going to call it pop front instead. If they said pop at item count -1, we're going to do pop back instead. So we'll just do pop front, pop back. This is the last node's index, so that's fine. Otherwise, we're going to need to walk to item number 2 or whatever they were asking for. So we have that in here. We're not going to use this return statement. So this is what we have. What's going to happen is we're going to delete this guy, and we're going to have to update these 2 pointers here. Now, we don't want to do the delete first because then we'll like lose track of the previous and next item. So let's go ahead and make another couple aliases just to make it easier. We'll do a before, and we'll point it to the item in before it, and we'll make a next, or let's say after. And we'll point it to whatever item comes after. So let's do that. Let's do just a doubly linked list node. Pointer before is equal to our pointer current, pointer previous. Pointer after is equal to pointer current, pointer next. So then we have these two to help us out. Now at this point we can go ahead and just delete pointer current, because now we have pointers to the before and after. We don't have to worry about losing track of them. So we can say delete pointer current, and we have to update the pointers. So what this is going to look like is let's make a white rectangle to show that this thing was destroyed, and now their pointers are just pointing to nothing. So the befores, new next, needs to go to the after. So we'll do that. Say pointer befores, new pointer next is equal to pointer after. The afters, new pointer previous, points to before. So pointer after and pointer previous is equal to pointer before. And don't forget to decrement the item count. Okay, and now all of the tests are passing. Go ahead and refresh this. All of that's good. We are now done with the linked list.